Next question. The diagram above shows water waves, below shows water waves approaching a straight barrier. A pupil records her observations of the reflected waves which are shown in the diagram below. So you can see them, they're going in here, going to hit the barrier. And this pupil is suggesting that they're going to come straight back out again. What two errors have been made by the pupil in the second diagram? So if I maybe go a wee bit wider in this, it's usually I'm going the wrong direction. You can see the two waves at the one go there. And you can see, first of all, this is a reflection idea. And you know that the reflection idea, the wavelengths shouldn't change. It's only in refraction that wavelengths change. So that's your first problem there, that wavelength should not have changed. Now the second thing is, of course, that if that is the direction that the water waves are coming in along there, and they hit the barrier, and you drew a normal in here, then they should come out this way here, the direction that the pen's facing, and your wavelengths should be, or wavefronts should be, perpendicular to that. So obviously the direction's wrong. So direction is not correct. Now you could draw the correct direction in the diagram if you wanted, but on the next page, they've asked you to do that. So using the space below, show how the reflected waves would actually have travelled. I'll just straighten that up for you again. So there's your waves going in. So I'm going to draw a line here. And again, I'll just use my wee piece of card to make sure I've got a good right angle. And so there's my ray going in. I'm going to draw a normal here. Again, we'll use a piece of card. And if you've got your examining card on the desk beside you when you go into your exams, your candidate number card, you could just use it. Make sure you've got a right angle. And then if you estimate, or even better, use a protractor, you should be able to see the angle. Now I'm going to have to guess. And it looks kind of like 45 degrees to me, maybe a little bit less. So I'm just going to draw a line down like this. Now that's the direction of the reflected waves are travelling in, but now I have to draw in my wavefronts, and again I'm just going to make sure I'm getting right angles there. Okay, and I'm going to draw them, and they should be roughly, let me see, about 2 centimetres apart. So the next one's going to be down here, like that. And even if you draw just 2 of these, it says at least 2 wavefronts. You could draw a third if you wanted. On down a bit. I'm going to guess this one. They're quite happy. So what they want is that the wavelengths are unchanged, so that this lambda is the same. That'll give you 1 mark. And then the direction now, it'll say by I in the mark scheme, which is fine. Those two angles look more or less the same, I and R. I being incident angle and R being reflected. So there's your second mark for the direction being correct. Part E. A microphone is attached to a cathode ray oscilloscope. A tuning fork is struck beside the microphone. The resulting waveform that is immediately seen is shown in the diagram below. As you watch the waveform, what changes would you expect to notice? Explain the change. So, the tuning fork struck beside the microphone, but there's nothing there to sustain the tuning fork. So what you would expect is that the tuning fork, it will get quieter and quieter, like that there. And so what do you notice happening there? You can see that the amplitude of the wave is getting smaller and smaller. So your observation is that the amplitude gets smaller. And what's the reason for that? And that's because the wave is getting quieter, or the sound is fading away. What would not change as you watch? Explain why. And the answer there is the frequency or pitch would not change. But what do you actually see? You see the wavelengths, and the wavelengths won't change. And explain why. You're using exactly the same tuning fork. So tuning fork is the same. Or the tuning fork doesn't change, or something like that. Last one, a second tuning fork is struck beside the microphone and the resulting waveform is seen below. What two things can you say about the note that is produced by the second tuning fork compared to the first? So if I hold the first one over here just beside it, we can see that both of them on the one page per minute. And so what two things can you say about the note? Well, first of all, it obviously looks a lot higher. But the second thing you can say there is they obviously haven't changed the number of peaks that are in that screen. So that means their frequency is the same. And if I just set this over the top, I don't know if you can see through or not. But you can see, I think you can see through. Underneath you'll see the bigger one. And you can see that there's the same number of waves in the same space. And so the two things that we're going to say that are the same, amplitude is larger or it is louder. I'm going to put just beside it amplitude larger. And the second thing, what can you say about the note produced, is that it has the same frequency or pitch. And that's the end of the past paper, the waves and sound questions for your past papers. Thank you.